Hi everyone, my name is Elizabeth Lees. I'm a senior math and dance major, and today I'm going to be talking to you about Dr. Boucher and I's research on the Collatz conjecture. So to give some background on the problem, the Collatz conjecture was first stated in 1937 by Lothar Collatz, and it's an open problem in math, which basically means that it hasn't been proven yet. And what the conjecture says is that if we take any natural number, so 1, 2, 3, 4, 5, and so on, and if our number's even, we're going to divide it by 2. And if our number's odd, we're going to multiply it by 3 and we're going to add 1. And then if we take our resulting number after doing that and repeat it, eventually after we do this so many times, we're going to get to the number 1. So we can write this up mathematically. And basically all this says is for n that's a natural number, we can define this function to be f of n equals 3n plus 1 when n is odd and n over 2 when n is even. And then the sequence n, f of n, f of n, and so on, contains the number 1. So we're going to look at an example where we calculate the sequence for n equal to 3. And that basically means we're just going to look at what happens when we start with the number 3. So we're going to start by finding our first piece, which is f of 3. And since 3 is odd, we're going to use that formula 3n plus 1 from the previous slide. So basically all we're doing is where we see an n, we're going to plug in a 3. So we have 3 times 3 plus 1, which gives us 10. Now we're going to take that number 10 and we're going to put it in as our next term. So we're going to use that as our input. And since 10 is even, we're going to use that formula n over 2. And 10 divided by 2 is 5. So then that will become our next input. And we'll continue doing that. And when we plug in a 5, we get 16. 16 gives us 8, 8 gives us 4, and so on until we get the whole way down to the number 1. So that gives us our sequence, and we can see that we do get down to the number 1. And when we look at examples like this, it's easy to see the conclusion of the conjecture, but looking at the big picture, it's hard to prove that that works for all natural numbers. So we can write these starting values of n as a sum of two natural numbers. And when we do that, we can just say let n equal x plus y. And then when x and y are both even, that f of n is just f of x plus f of y. When 1 is even and 1 is odd, then that's 6f of x plus f of y. And then when they're both odd, it's f of x plus f of y minus 2 all over 6. So we're going to look at another example for this. And this is going to be calculating f of 14 with 14 as a sum. So one way we can write this is 14 as equal to 7 plus 7, right? So 7 and 7 are both odd, so we would use that formula that says they're both odd. So when we write this up, we would say, okay, it's f of 7 plus f of 7 minus 2 all over 6. And because the 7s are both odd, then we're using that 3n plus 1 formula to get those 22s, that 22 plus 22 minus 2 over 6, and that gives us 7. And then another way we could write that up is with two evens, which would be 4 plus 10, and that's way is much easier, as we can see. And that would give us f of 4 plus f of 10, which would just be 2 plus 5, because we would just be dividing both of those numbers by 2, and that gives us 7. And so both of these options give us exactly f of 14 equal to 7. And we just wanted to look at this as a way to maybe simplify some numbers that have a lot of steps. You know, with a number like 14, it's simple to get to that 7, but some numbers are much bigger and it might be easier to break them up. So similarly to the way we can write sums, we can write those starting values of n as a product of two natural numbers. So when we would do that, we would just say to let n equal x times y. And then if they're both odd, it will be f of x times y minus y plus 1. And then in any other case, so 1 even, 1 odd, or both even, it would be f of x times y. And our goal in looking at the product specifically is we were hoping that we could use prime factorization to determine the number of steps it would take to get to 1 for certain numbers. We haven't gotten super far in looking at that, but I know that's something we want to continue looking at as time goes on. So we're going to look at that same f of 14 example with products. So we can rewrite 14 as 7 times 2. And then we would use that formula that was f of x times y. So we'd have f of 2 times 7, which is equal to 7. And we know from that last example that f of 14 is equal to 7 because it's just 14 divided by 2. So one of the things we worked on this summer that we wanted to do is we wanted a way to sort of visualize these sequence points and the input and output values as like graphs. And we wanted it to be in a way that other people could use, that was easy to access and user-friendly. So we decided to do this in Desmos because it's just a free online graphing calculator that anyone can get to. And we were able to develop a tool that automated those graphs for starting numbers 1 to 25. And then it's pretty cool. There's like a slider you can use, and we're going to look at it. But yeah, I guess let's just look at it. So here, when we look at our slider here that I was just mentioning, we can see for the different points our graphs here. So if we go back to this example that we looked at the beginning with with our starting number equal to 3, we can see our points here, where how we bounce around. You know, when x is 3, then it's 10, and then we divide by 2 and get 10 and 5, and then bounce back up here, 5 and 16, and then 16 and 8, and then it slides right down to 1. And then once we get to 1, forever and ever, it's going to go 1, 4, 2, 1. So then something we can do with this is we can just sort of play it and watch the different graphs pop up for 125. We can also stop and pause it. I'm going to slide it over to one that has some different numbers here. And then I can come down here and look, okay, so when we start at 15, this will tell me what my different sequence points are. So 15, then we have 46, 23, 70, 35, and we'll continue all the way down until we get to 1. And we can look and see in here what those different points are. So it's a pretty cool tool, and I would like to keep working on expanding it to see if we can get more numbers in there and see if there's a way to make it just smoother. But that's definitely a work in progress. And then the last thing, something we're currently working on, something we want to continue working on in the future. This is super blurry, I'm sorry. But this is a little chart that I made that basically it says n, which is our starting number, the total number of steps it takes to get to 1, and these are numbers that we know for sure go to 1. And then our 3n plus 1 steps, our n over 2 steps, and then the difference between our n over 2 steps and our 3n plus 1 steps. And basically what intuitively we sort of thought is that, you know, if it's going to decrease down to 1, there's going to have to be more decreasing steps than increasing steps, which means that there's going to have to be more n over 2 steps than 3n plus 1 steps. So that's something that we're working on trying to prove. And then another thing in here is there's just lots of interesting patterns. Like if we would look at something like, it's really hard to see, but this green strip here says there's a difference between those n over 2 steps and 3n plus 1 steps of 5. So if I track down all those 5 differences, here we have a total number of steps of 9, then a total number of steps of 7, and then when we jump down to the next one, which isn't pictured here, it would say the total number of steps is 5, and that pattern continues. So there are lots of patterns in here to look at, and it's just, you know, pulling out exactly what those patterns are and trying to figure out why they occur and getting them down in words. So that's something we really want to work on. And then there's this chart down here that directly relates to this one here, this graph. And basically on the bottom here, these numbers that are really teeny tiny are n numbers, so like these starting numbers. And then here is on the y-axis is the total number of steps. And this blue line is our 3n plus 1 steps, and the orange line is our n over 2 steps. So I thought it was really interesting that these are almost exactly the same shape as you go across. So I think that's something also to look at and see what's going on there. But yeah, that's all I have for you today. Thank you so much for watching.